Hi everybody, in this video we're going to introduce the last two equations that we're going to be discussing and considering in this unit about gas laws. There they are. The first one is the ideal gas law, PV equals nRT, and the second one is Dalton's law of partial pressures, which is given as P total is PA plus PB plus PC plus, you get the point. So what do these equations mean and why are they useful in chemistry? That's our goal in this video. You might remember at the beginning of the unit I said that we can summarize most of what we're going to study in just one equation, PV equals nRT, the ideal gas law equation. And we guessed a little bit about what the variables in that equation are. But then before we use this PV equals nRT equation, I just proceeded to talk about all these other gas laws like Boyle's law, P1V1 equals P2V2, and Charles's law, which can be written as T1V2 equals T2V1 and so on. And these are really all kind of summarized in this ideal gas law. You'll notice that there's no ones and twos here, but when we write P1V1 equals P2V2, we mean that it also equals P3V3. In other words, P times V is always the same number, as long as N, the number of moles, and T, the temperature, are the same. In this equation, the letter R is just a constant called the ideal gas law constant. So this equation is essentially saying P times V is a constant. Now, if two terms are on the same side of the equation in the ideal gas law, that means they are inversely proportional. Of course, the only way that P times V can be constant is if the bigger the pressure is, the lower the volume is. Now, if two terms are on opposite sides of this formula, like temperature and volume, then that means they're directly proportional. Where all other things held constant, the higher the temperature, the higher the volume. So the ideal gas law really summarizes all of the individual gas laws we've talked about so far. When we're using PV equals nRT, we have to pay careful attention to units. R is an ideal gas law constant. That's just a number that you're going to need to look up or remember or be given. However, the pressure and volume are going to determine, and the temperature, the units that we're going to be using. Now, volume we're always going to be using in liters, and temperature, as always in this unit, is going to be in Kelvin. But we've talked about many different units of pressure. Typically, we're going to use pressure units in either atmospheres or kilopascals when we're using PV equals nRT. And depending on which units of pressure we use, the value of R will change. If you're using atmospheres for your pressure measurement, then the R value is 0.0821. Now the units of R are quite complicated. They are liter atmospheres per mole Kelvin in this case. Now don't worry about how complicated those units are. It's essentially just an equation fixer. So there's no other operation to do here other than to plug in that numerical value for R. If, however, the pressure is given in kilopascal, then the R value is 101.3 times greater than that, 8.314, and the units are liter kilopascal per mole Kelvin. You could even figure out an R value for torr, or millimeters of mercury, but these are the two R values that are most commonly used. So R is simply a constant, a number that you'll need to look up. Since volume is always going to be in liters and temperature is always going to need to be in Kelvin, and of course is in moles, the pressure units are ultimately what determine which numeric value of R we use. Now those units are very strange. We can picture 5 meters or even 5 meters per second. But picturing 5 liter atmospheres per mole Kelvin is not something that anybody can do. This quantity is really just a constant that allows all of the other units to cancel out. For instance, if we rearrange the equation to solve for V, that would be nRT over P. All the units cancel except for liters. If we rearrange the equation to solve for N equals PV over RT. All of the other units cancel except for moles. Let's try a few practice problems and see how this equation is used. All right, so the questions we're going to look at are on a worksheet which I've posted in Classroom as well. This worksheet is not due for credit, but I would recommend that you try these problems before attempting the checkpoint, which is going to have similar questions on it. Let's start with the first question here as an example. Before you may want to just watch this example before you try the next few on your own. It says it's not safe to put aerosol containers in a campfire. Well, that should be obvious, I hope, because the pressure inside the canister gets very high. If a 1 liter canister holds 2 moles of gas, well, let's see. We know the volume, 1 liter, given to 3 sig figs. We know the number of moles, N is 2, given to 3 sig figs. At 212 degrees Celsius, remember that we want to convert that to Kelvin, and I think that 212 plus 273 is going to be 485 Kelvin, and I can actually include an additional significant figure there since, well, we're going to always add 273 even, so we're going to keep it to the nearest whole number just for simplicity's sake, and only ever add to the nearest whole number kelvins, even though that conversion factor is technically adding 273.15. We're going to just use 273, so I'll truncate that to this number of significant figures so that we just have whole numbers in our temperature. And it says what would the pressure inside the can be. Now, pressure is my unknown variable, and if I want to take PV equals nRT and rearrange to solve for pressure, then PV equals nRT becomes P is nRT over V, right? Divide both sides of the equation by V. And I have everything else in my list that I need except for the R value. Now let's see. The R value is going to be the one that gives me the pressure units I want. For instance, in this case, since we are solving for pressure, we can use any R value we want. If we use the 0.0821 R value, that's the one which is in liter atmospheres per mole Kelvin, then of course when our final answer is calculated, it's going to be in atmospheres. If instead I had used the R value, which is in liter kilopascal per mole Kelvin, which is 8.314, then I'd get a different answer numerically, but of course my answer will be in kilopascal. So in a case where you're solving for volume, you can actually use whatever pressure units you want, or solve for whatever pressure units you want, and we should get the same answer in either case. Let's see what we get. So in the first case, I get an answer in atmospheres, and I get rounded to, let's see, 3 significant figures. Since my answer is 79.637, I'm going to round that to 79.6. That's a tremendous amount of pressure. 79.6, almost 80 atmospheres. No wonder the can explodes. That's what I get if I use this R value. All the units cancel except for atmospheres. If I use this R value, I get the same correct answer, but of course it's expressed in different units. 8,060 is what I get here, and that's an answer in kilopascal. Notice that 8,060 kilopascal is 80 atmospheres. So we get the same answer in each case, but it's only the units that we've chosen which are different. Let's look at the second problem, where the pressure is given in atmospheres. And in this case, of course, that's going to dictate what R value we should use. In question number 2, it says, how many moles of gas are in a 20-liter scuba tank? Okay, the number of moles of gas is our unknown. If the temperature of the canister is 300 Kelvin, temperature's already given in Kelvin, and it looks like we have 4 sig figs in that case, and the pressure is 6.5 atmospheres, so only 2 sig figs here. Now the R value that I have to use here, unless I want to convert this pressure, is going to be the R value which has atmospheres embedded in it, 0.0821 liter atmospheres per mole Kelvin. Now let's see. I want to rearrange PV equals nRT to solve for N. That means I'm going to divide both sides of the equation by the quantity RT. Notice that that is the quantity RT, so pay attention to order of operations, and I'll go ahead and plug the numbers in and round my answer to 2 significant figures. Let's see what we get. The answer I get in moles is 5.278, rounded to 2 significant figures. That would be 5.3 moles. Now I did that by taking my pressure, 6.5 atmospheres, and multiplying by my volume, 20.0 liters, and I forgot to list the volume in the shopping list there. But then I took that product and I divided by the product of R and T. Dividing by the quantity RT gives me 5.3 moles. There are two more problems on this page, and I'd recommend pausing the video here and seeing if you can solve them before unpausing it and see if your answer matches the solution I'll show in just a moment. So here are the solutions. The first one is a little simpler than the second. You can see in question number 3 it's solving for temperature, and in question number 4 it's solving for volume. In question number 3, I've rearranged the equation to solve for temperature, PV divided by the quantity nR. And because the pressure was given in atmospheres, I went and used the R value which corresponds to atmospheres. Now I've rounded my answer to 2 significant figures since there were only 2 significant figures given in the pressure. In question number 4, there is a curveball here in that it gives you a mass, and we need to convert that to a number of moles. So I've done a gram-mole conversion here for CO2 using the molar mass of CO2. Remember, N has to be in moles. Volume is going to be in liters. Temperature is always in Kelvin. Pressure can be in either kilopascal or other units of pressure. In this case, since the pressure is given in kilopascal, I need to use the R value that has kilopascal embedded in it. I've used that R value, solve for volume, and I've rounded my final answer to 3 significant figures since there's only 3 significant figures in my converted temperature. Let's look at one more practice problem. So the last problem that I want us to consider is this one. What is the volume of 1 mole of gas at STP? Now remember, STP stands for standard temperature and pressure, and that means 273 Kelvin, the freezing point of water, and 1 atmosphere of pressure. If we rearrange the equation PV equals nRT to solve for volume, and the number of moles is 1, R, if we're going to use the pressure units of atmospheres, which is going to be simplest, will be the 0.0821 value. The temperature is 273. We get the same answer regardless of what gas we're talking about. CO2 gas, O2 gas, neon gas, methane gas, all of them occupy 22.4 liters per mole of gas. Now, the reason this is called the ideal gas law is because ideally this would be a predictable molar volume of a gas in every case. But in fact, intermolecular forces and very, very low temperatures and high pressures can cause this to behave a little bit non-ideally. So when we say the ideal gas law, it is an idealized version of gas behaviors that makes a few assumptions. It assumes that the volume of the particles themselves is negligible compared to the spaces in between the particles, and it assumes that there are no intermolecular forces of attraction, which may be a reasonably fair assumption for a gas like neon or helium, where only relatively weak London dispersion forces operate, but in a gas like water vapor, where there's significant hydrogen bonding forces operating, then the ideal gas law fails to make accurate predictions. If we ignore intermolecular forces and some of those other considerations, however, the molar volume of a gas is 22.4 liters per mole. And that's an important and helpful number to keep in mind when many calculations. So we've talked about the ideal gas law, which is the first of the 2 equations I said I'd introduce in this video, PV equals nRT. The second one is very simple, but just to summarize, in the ideal gas law you may be solving for pressure, volume, number of moles, or temperature, and you'll need to select the R value which matches the pressure units you're using. In the second equation, Dalton's law of partial pressure, we're simply looking at a principle that emerges when we're considering a mixture of gases. In order to talk about Dalton's law of partial pressure, we need to understand what partial pressure is. Partial pressure is the pressure that one component of a mixture of gases would exert if that one component were alone in a container. So perhaps we have a container that has methane gas and water vapor in it at a fixed volume and a total pressure of 1 atmosphere. That 1 atmosphere of pressure is due to both the methane and the water vapor that are present. If they, for instance, each exert an equal amount of pressure, then the partial pressure of the water vapor is half an atmosphere, and the partial pressure of the methane is half an atmosphere. Dalton's law of partial pressure is simpler than it may seem. In this first picture, you can see that the 4 moles of gas on the left, depicted by those 4 blue particles, exert 2 units of pressure, as represented by the 2 weights that are required to keep the piston at equilibrium. In the second picture, you can see we've got 10 moles of gas of a different substance, and those 10 moles, it looks like, are exerting 5 units of pressure. Now, if I took both of those different amounts of gas, the 4 moles on the left and the 10 moles in the middle, and I put them in the same container together with the same volume, what would the total pressure be? Well, the partial pressure of gas A, the blue one, was 2, and the partial pressure of gas B, the orange or red one, was 5. So the total pressure exerted by this mixture of gases at the same volume would be 7 units of pressure. The total pressure in a mixture of gases is simply the sum of each of the partial pressures exerted by each gas component. That's what P total equals PA plus PB plus PC ... means. So Dalton's law of partial pressure is most often applied to a particular circumstance. Here again is an example of one gas at 5 kilopascal, another gas exerting 20 kilopascal. If they're both contained together in the same container, then a total pressure would be 25 kilopascal. Why this principle is useful is that we'll often want to know what the pressure of one of those gases is, or the partial pressure of one of those gases is. Of course, if the total pressure in the container is 25, and I know that only 5 kilopascal are due to gas A, the remaining 20 must be due to gas B. This comes up most often when we're collecting gases in a lab over water. The collection of a gas over water is a common way of trapping a gas inside a container. And this experimental procedure shows you how that looks. In this case, we're heating potassium chlorate with a little bit of manganese dioxide as a catalyst, and oxygen is produced. We're collecting that oxygen over water. And because we're bubbling it through water, we're going to introduce water vapor into the container. Where it says oxygen plus water vapor, we not only have the oxygen that we're interested in collecting, we also have water vapor. If the total pressure inside that container is 1 atmosphere, and we want to know what the partial pressure of the oxygen is, we will have to subtract the partial pressure of water vapor from that total pressure of 1 atmosphere to determine what the partial pressure of the oxygen alone is. The partial pressure of water vapor at a particular temperature is something that can be looked up, and partial pressure tables for water vapor exist online and in textbooks so that people can reference those numbers. Very commonly in a lab procedure, we'll collect a gas of interest and we'll have to subtract the partial pressure of water vapor from the total pressure that we recorded in the lab in order to know what the partial pressure of the dry gas alone, so to speak, is. Dry meaning not including the water vapor. And we'll see this come up in a lot of gas laws, lab activities, and lab procedures. So that wraps up our discussion of these last 2 equations, the ideal gas law and Dalton's law of partial pressure. We'll see you next time.